We're going to solve a problem called find network delay time. So please read the problem on the screen and feel free to pause the video. This is an example from the previous statement. So think about let's assume that you're given this input and then you got this output. So think about how you got from this input to output and what kind of algorithms you can use. Once again, feel free to pause the video and think about what kind of algorithm you would use to solve this problem that we have learned from a class so far. So here's some thought process that I would like you to have, or at least that I would try to have. So first is what are the information, like critical informations, right? So we definitely there's some importance along with like source node target, and the time to reach source to target. And we also want to signify that we are looking for the time that the last network node will receive the signal because this problem states that all nodes to receive the signal, right? So it's not just one or two, it has to be all. And then here it also says if it is impossible, then return -1, right? So if we cannot we are also given the starting vertex as a parameters, but then from the starting vertex, if we cannot reach all the nodes, some of the nodes in our graph, then we should return -1. So it could be some constraint, right? So we are thinking like how can we achieve this, right? And then what kind of algorithms we can use. What came up to my mind was that essentially what we are looking for is the shortest time. We want to look for the shortest time that all the nodes will receive such signal, right? We don't want them to give like the slowest time that that the network will receive the signal, and then that's not what the problem is wanting, right? So we want to look for shortest time. It kind of sounds like oops, Dijkstra's shortest path. Even though we talk about path, but then the weighted could be in this case, which would be time could be alternative to the example that we have seen in class before, right? So I'm gonna do some example walkthrough. So here we know that k is 2. Oops, let me do a pointer. So we know that k is 2, which means that the signaling starting vertex is 2, like the arrow points. So here we don't have any predecessor and distance is 0 because you're starting from yourself. And now we are visiting 1, so we mark the predecessor and the distance 1. But we just clarifying that before we explore everything, you can give some kind of infinity value, just signifying that we have not explored this vertex yet. And we have talked about this already. And next, we are going to, now we are on the second inner array, right? So this again, the starting vertex is 2, and then the source vertex is 2, and then the target is 3, which is like this, right? And then the weight is 1. So which means that now we're going to update the predecessor in distance to 1 because 1 is less than infinity, right? So now this has been processed, and then now we're going to now we're going to work on the last array, last list, which would be 3, 4, 1. So here from 3 to 4, we know that 3 has a previously distance 1, right? But then we have to go 1 more. So basically what it represents is from the source vertex, how far is 4, right? Is actually 2 away. So we can mark the distance as 2 is less than infinity, right? But then as we have seen in the lecture that if that distance is the updated the new distance is greater than the distance that we have seen previously, then we don't want to update that, right? So this is a general algorithm. That's why you would get 2, which is that's the time that all the network nodes will receive the signal. So that was a quick example walkthrough. So you can come up with some other cases, more simple or more complex cases that could help you develop your algorithm. So we can think about how do we know if all the nodes are reachable from the node we begin signaling, right? So I guess the simplest way that I thought about is we know that we were going to mark all the vertex distance as infinity, right? So why don't we just loop through them later on, as we have to find in order to find the shortest the maximum the maximum time, like which is in I say maximum times, but the minimum time that all the nodes will receive the signal, we will have to go through our some kind of data structure anyway, right? Like at least O of n, which just wants to figure out what is the maximum time among that, right? Among that nodes. So here we can just check while we are looping through that if the node you're checking has a distance affinity, then it hasn't been visited. So you can just immediately return -1. So we know how to do that, right? And this is a brief pseudocode how you would implement this. So here's the method header here. First, you can create some kind of data structure that will keep track of source node and its neighbors, right? Like we have designed in using a table, like a physical table like we have seen before. So while we're iterating through the inner array in times, because you can see it's 2D array, so we can mark the key as a source vertex and the value as a data structure that stores the target and delay time, right? So that'll be easier for us to process. Um, and we can essentially sort by delay time. And then we can create a data structure that signifies initial distance for all nodes, which is infinity. That's just essentially the same as the physical like visual table that we just created it from the previous example. And we can run DFS that keep tracks of elapsed time. The idea of updating distance, that's essentially same as the idea of updating distance in the original algorithm that we had seen in the class. And then now we'll go through all values of updated distance. If encounter infinity value, then return -1. Else we can keep looking for maximum of distance as it is the longest time it took to receive the signal, right? So I hope that helped. And then here is a brief pseudocode that we actually mentioned in class. So maybe think about how this pseudocode and this pseudocode varies and how we modified in order to solve this problem from this basic ice stress that we have talked about in class. So yeah, have a great day.